Welcome back to another lecture of Physics 221. This is going to be our fifth lecture, and with this lecture we're going to conclude the chapter on multivariable calculus. So let me just do a quick recap of what we've done last time. So we've discussed the fundamental theorems of multivariable calculus. So we've seen a relation between the flux and area integrals and the volume integral. So the flux was basically taking the dot product of a field with the area element, and you could relate that with the divergence of the field. We said that flux represented how much of the vector field you're losing out of the volume. So it represents the source rate, sort of to speak of your vector field. And we have a similar interpretation for the line integral, the fundamental theorem of line integrals. So we said that if you have a closed path, again, this is something that you must keep in mind. These are really important conditions for these theorems to hold. And that is that, when these theorems apply, you have a closed path or a closed surface. You cannot apply them otherwise. Okay, so back to our point. How do you interpret line integrals? Well, first let us see what the line integral theorem tells us. The Stokes Theorem tells us that if you have a closed path and you take a line integral, it can be taken as an area integral as well. It's the area integral of a surface that surrounds this closed path, that has this closed path as a boundary. Now, typically in this course, you're not going to deal with these theorems very much. You're going to deal with the two-dimensional versions of these theorems, because finding these normal vectors in this theorem, it's not really straightforward. For most surfaces, it's really hard to find a normal vector. So you should just keep this in mind, because you're not really going to use them in this course. What you're going to use more are the 2D versions. But first, let's look at the interpretation of the curl, this quantity here. The curl of a field, if you have a velocity field, will give you 2 times the angular velocity. How's that? Well, you have, on the left-hand side, you have a closed loop. And if you have a vector field that goes like something like this, you can see that, this quantity will be positive. You can imagine that, these are the tangent vectors. There are tangent vectors to the curve, like this, and you take the dot product between the tangent and the field itself. So the interpretation is that the curl of a velocity field should give you the angular velocity. And this is something that is consistent across different fields. Even in EM fields, there is a relation between the curl of the electric field, which will give you time rate of the magnetic field. There is a really deep connection between the curl of the electric field and the magnetic field. There is some constant in here, but you don't really have to worry about this. This is another of the Maxwell's equations. Which one is it? This should be the Faraday's law, I think, that a moving charge produces a magnetic field. Okay, so that's basically the interpretation of curl. Now let's move on to the actual useful theorem in this course, which are the 2D versions. So I've already given you the statements of these theorems in the last lecture, if you remember. The statements were these. If you have a line integral, I claimed that you could convert it to an area integral of this quantity, partial xq minus partial yp. Now you might wonder, why did I choose this quantity specifically? Why is this combination really specific to this theorem? Well, the answer is that it comes from the 3D versions of this theorem. If you look at the 3D version statement for the line integral, let me just rewrite this. I'll have the line integral of a force field, say a force field over a closed loop gamma is equal to the area integral of the area enclosed by that closed loop. So you have a curve like this. Say it's going clockwise. This is gamma. And you have the area enclosed by this, say R. So the area R. So the theorem tells us that if you take the curl of F and take a dot product with the area element, one thing that I want you to notice here is that this is the normal vector. And I'm talking about a field that goes out like this. And you have a normal vector like this, n hat. And usually this is really difficult to find, this n hat. And also this is actually a flux integral, not an area integral. So, you know, there are deep connections already. You can see that you have a line integral that is related to a flux integral. But we cannot really go a lot in detail about this. We're just going to settle for the statement itself. Okay, so I want you to see that if F is, say, P, Q, R, where P, Q, R are the components of F, and P, Q, and R are, say, functions of X, Y, and Z. I want to reproduce this 2D version of this theorem from the 3D version. So I have a vector field with R equals 0, because in 2D you only have X and Y, right? Because you have the 2D plane like this, and you have the field completely lying in the 2D plane. This is X, this is Y. With the 2D case, you have a simplification. And what simplification is that? Suppose I have a closed curve like this, and I want to find a normal vector. Since this curve is entirely in the 2D plane, you can imagine that the normal vector goes outside this page or inside this page. This is another point, another subtle point that I want to get across to you, that the normal can be outside the page or inside the page. Depends on the application. Suppose I want to measure how much water is flowing in. In that case, I want, the inside of the surface to be the positive, because getting more water will increase the volume. And suppose if I want to measure the electric field, in that case, I have a charge Q like this inside some, capacitor, and the E field goes outside like this. E field goes outside. So in this case, this normal vector, the one pointing outside, should be positive. Depends on your application, right? So that's a statement on the normal vector itself, which you won't really need here because you're not going into the 3D version of this theorem. Well, the point is that the normal vector, when the field is entirely in 2D, is either plus or minus k. So, it's a simplification of some sorts in 2D. So I just want the kth component of this, because, if I have a vector and I dot it with k, I'll get the z component of that vector, right? So let's look at what the z component of curl F is. If you remember, in Cartesian coordinates, it was nothing but this. I, j, k on the first row, and then you had partial x, partial y, partial z, and p, q, r. These are the components of F. Now, we said that r was 0 because the field is entirely inside the 2D plane, so we could take this as 0. And if I calculate the kth component, because you're dotting curl F with k, what will I get? I'll just need this component here, which is what I was, doing right here. I'm just writing this again. Okay, so what will I get? The kth component, let's denote it like this. The kth component is this one. You can compute the determinant like this: partial x of q minus partial y of p. This is what you'll get by doing curl F dotted with k. So the integrand in the theorem, this is from the 3D. So if I'm moving to 2D from this 3D version, what will I get? I'll simply get the line integral on a closed loop of f dot dr equals the area integral. Suppose the loop is called gamma. So you'll loop over the, you'll take the integral over the area enclosed. Again, the area enclosed is this thing. And the curl of f, only the kth component of f is this one. So I can just copy this. And paste it here. And then I just add the area element, d sigma. D sigma is usually dependent on your coordinate system. So d sigma can be dx, dy, or if you're in the cylindrical coordinate, you might have r, dr. We're talking about the cylindrical surface, so you're not changing r is fixed. So in that case, you'll have r d theta dz. Okay, this is another conversation to be had later in this lecture. So you get the idea. This is the 2D version. Isn't this the same thing that we derived? That we stated last time? Let's have a look. Partial xq minus partial yp. And we have here partial xq minus partial yp. Exactly the same thing. So you see that the 2D version is a simplification of the 3D statement of the 3D Stokes Theorem. So these things are fundamentally connected, the 2D statement and a 3D statement. In fact, you can actually extend these theorems to arbitrary dimensions. There is a version of Stokes Theorem, suppose say in 7 dimensions or 11 dimensions. String theorists, they live in different dimensions each day. They live and breathe with these theorems. Well, anyway, okay, this is the what do they say, the duality of these theorems between 2D and 3D. Okay, so the next thing I wanted to talk to you about is conservative fields. The idea of conservative fields. We touched upon this, I don't remember, in the last lecture or the first lecture in the multivariable calculus series, that when we were discussing line integrals, suppose I have a path like this that closes it in on itself, starts and stops at the same point, and it goes like this, and you have some vector field like this, some vector field. We said that one of the fundamental theorems is that if I have a vector field f, which can be expressed as a gradient of some scalar function phi, which in turn is a function of x, y, and z, then I can write, and it starts from a and b, starts at a, ends at b. In this case, they're the same. I can write that phi, this integral equals phi b minus phi a. Now, if I make this a closed integral, I told you that this is not always 0. There's a specific, condition that it has to satisfy. And that condition is actually that the phi, function phi, must not have any singularities or discontinuities inside this region R. So phi doesn't blow up. Say this is, I have a function phi equals 1 over x. You see that at x equals 0, phi blows up to infinity, right? So if I have a region that has the region has x equals 0, then I cannot use this theorem. I cannot say that the line integral gives me this. So the idea of conservative fields is that no matter where you're starting, no matter what path you're taking from a point A to a point B, the work done by the field is the same. I can take this path, or this path, or this path. And an example of this kind of field is gravity. Electric field is also an example of this kind of field. Now, if you remember from your physics courses earlier in Physics 101, 102, that you had this idea of a potential, right? You had the electric potential V, you had the gravitational potential mgh, and for a point charge V was kq over r in electrostatics. Now, to find a potential, a field must be conservative. This is a crucial thing. As you have experienced in Physics 101 and 102, dealing with potentials is much easier than having to calculate trajectories. Like, I have a ramp like this and a ball that is rolling like this and moving down. If I wanted to calculate every single detail, the velocity at each point in time, I need to go through Newton's laws and everything. It's really complicated. But if I have the potential, I can just do potential at A and potential at B. That will give me the total energy at a given instant of time. And from the total energy, I can relate kinetic energy and find the velocity. So dealing with potentials is really something fundamental in physics. Most fields in physics are conservative, but there are fields that are not conservative and they're nasty, really nasty. So what I wanted to point here is that this statement about conservative fields can be related to Stokes Theorem. And I'm going to show you how now. So the Stokes Theorem gives me, I'm just restating the Stokes Theorem here in the 3D version. If I have a closed path gamma, this value of this integral is simply the curl of f, the flux integral of curl of f with the area enclosed. So suppose I have this path gamma, and the area I'm talking about, area enclosed, can be this one, the one immediately inside the plane, or it can be outside here. Again, this is something really nice, and we cannot really discuss this in a lot of detail, which I really regret. Okay, so we want to relate conservative fields with this. So conservative fields implies that when I have a closed path, I'll have phi b minus phi a, b equals a, so I expect this to be 0 if phi is a well-behaved function, not some pathological function that mathematicians come up with. Oh, they're quite devilish. They can find phi that doesn't work with this theorem. Well, anyway, if we put that aside, if b equals a, then I would expect that this line integral, along the closed loop gamma, will be 0. Now, if this is 0, what does this tell us about this side of the equation? These are not 0 because, usually, in generally speaking, n is not 0, sigma is not 0, so it's obvious that this must be 0. So if a field is conservative, by our definition, that is, it's path independent. Let me write this down. Path independent implies conservative. The definition really comes intuitively because, you see that the gravity force doesn't depend like which path you take. If you're on the earth and I drop from this height to this height, the velocity I gain is the same no matter whether I'm going this way or this way. As long as I'm moving from this height to this height, the total energy I get is always the same. So it's an intuitive definition of conservative fields. Well, anyway, I wanted to tell you that curl of f is equal to 0. Now, if you remember back when you were discussing vector analysis, that I told you that, if I have A cross A cross Well, that I was about to refer you to the box product, which is we actually need the cross product. A cross B equals 0 if A is parallel to B, right? So similarly speaking, gradient cross gradient of some scalar function is also going to give you 0. And you can look at this like this. If I take just gradient cross gradient on its own, I'll have I, J, K. So what I'm doing here is I'm crossing gradient with itself. In a vague sense, the gradient operator, the del operator, is like a vector. If I have two vectors that are pointing along the same direction, the cross product between those two will give me 0. So my point here is that if this product between del and f is 0, it implies that f is actually the gradient of some scalar function, the potential, right? So I can write that if I find that the gradient of f, the curl of f is 0, then f is actually some gradient function. This is equivalent to saying f dot dr equals d phi. How is that? D phi is what? Partial x of phi dx, partial y of phi dy, partial z of phi dz. Now if I imagine that I take the gradient of phi, what is this going to give me? This is simply partial x phi I plus partial y phi j plus partial z phi k, and dxi, dyj, dzk, that is nothing but dr. So this quantity here is simply d phi, the gradient of phi, times dotted with dr, and this is nothing but f dot dr. So you can see that f equals gradient of phi dotted with dr. So again, this is a statement of being conservative. So I'm giving you three different statements. One is that the work done by the field, the line integral, is path independent. Second one is that curl of f is equal to 0. And the third one is that f dot dr is an exact differential d phi of some scalar function phi. So these three mean the same thing. They're telling you the same, giving you the same information about the field, that the field is conservative. Now let's look at this in action. I want to give you an example of checking for whether a field is conservative or not. So the first example, I'm given two different fields, f1 equals 2xz I plus yj plus x squared k. Again, this is the notation that we discussed. This means a vector, and I have f2, another field, which is yi minus xj. So z is 0 basically. Now the question asks me, which is conservative? Okay, so we have defined conservative fields to be either of these three. Now the most obvious thing, since you're not given any path, like I'm not given any path, check the line integral over this closed path and tell me if the line integral gives me 0, whether this is 0, f dot dr is 0. I can use this, I can find the line integral, but it's not really the most easy way to do this, to solve this problem. The easiest way is to just take the curl. I take the curl of f1 and I see if it's 0. If it is 0, it's conservative. Well, there's an asterisk in here because if the function is divergent inside this region, if the field is divergent, goes to infinity, then it's not going to, or if it's discontinuous, even in some cases, if it's discontinuous, you cannot find a potential. Well, anyway, that's technicalities. You don't have to worry about it in this course for the most part. Okay, so I have partial x, partial y, partial z, 2xz, y, x squared. This is the field I'm given. Let's quickly do this. I'll have this product of this minus product of this. The ith component is partial y of x squared. X squared is treated as constant, so it's 0. Partial z of y, same thing, again 0. And the next thing, I must take minus j times, so in this case I'll have to take these two, right? The product of these two, which is this times this, partial x of x squared is 2x, and partial so partial z of 2xz is going to give me minus 2x, because this is subtracted. This is again 0. And similarly, if I take the kth component, we just erase these things. The kth component, I'll have to multiply these two and subtract it from these two. So partial x of y is 0, partial y of 2xz is again 0. So I can see that it's 0. All of these gives me 0. So I can immediately conclude f1 is conservative. And honestly, you can see that this is a well-behaved function. This is just polynomials. Polynomials are your best friend. They always behave nice. So f1 is definitely conservative. Let's look at the second one, y and x. Let me make sure this is okay. This is y and minus x. Okay, let's find out whether this is conservative or not. Gradient, the curl of f2 is I, j, k, the usual thing. And I have x, y, minus x, and 0. Okay, let's do it. This is going to give me, the ith component is 0 minus 0, which is 0. The jth component, the jth component is going to give me 0 minus 0, again 0. And the kth component is going to give me minus 1, and partial y of y is again 1, and you're subtracting that. Minus 1 minus 1. This is going to give me minus 2k, and this is not definitely 0. So you can conclude that f2 is not conservative. Okay, now let's move on to a different kind of exercise. We want to now apply Green's theorem in the plane. Green's theorem in the plane, which is this one, the one we discussed. The one we discussed here, the 2D version of the Green's theorem. And we're going to use it to solve line integrals. This is the kind of questions that you'd be expected to answer in your tests and final. The flux is not as important. It's just the same thing. You just look at the statement of flux. This is the flux integral. If you have a closed loop, this is how you calculate flux. Or this one. If you know how to calculate one, the other one is identical actually. You're doing an area integral basically. It's just the integrand is different. So I'll be focusing on line integrals, but the flux integral is just an extension of this. You're just integrating different things. At the end of the day, you're doing area integrals, which we have discussed in the first lecture of this chapter, doing area and volume integrals. Okay, so let's do an example now. Our first example goes something like this. I have an integral c over a path c, and they're giving me this expression here, x squared dy. They're asking me to compute this integral. They're not telling me that this is related to any field, but we can interpret it that way, of course. And the c they're giving me is in the 2D plane. If this was in 3D, you would have been in trouble, because finding the normal in 3D is exponentially difficult than 2D. Okay, so anyway, the path they're giving me goes something like this, from 1, x equals 1, to x equals 4, and y is a function like this. So I'm going counterclockwise along this, and this function is y equals 1 over square root of x. Okay, so this is the area integral. This is the area under the curve. I'm getting ahead of myself here. Okay, usually how do you find this? You express y as a function of x, and then you find dy, and you do some derivatives here, and then you find an expression. You convert this with the chain rule. Now that is really going to be a difficult thing here, because you have 4 different paths in here that I have to do, 4 different integrals that I have to do. Is there a better way to do this? And the answer is yes, you have a better way to do this. Let's imagine that these things are components of a vector field, specifically f equals m n 0, because you don't have any dz part in here. So this is simply xy, x squared, and 0. Now, how do I apply Stokes Theorem in here? If I apply Stokes Theorem or Green's Theorem in 2D, but let's start from the Stokes Theorem. This line integral, this closed line integral, again, this is a really important thing that you have to satisfy. The closed path, the path must be closed. You cannot apply Stokes Theorem if the path is not closed. We'll do an example that illustrates this later. Now, the important thing here is this is equal to the flux integral of curl of f. And as I said, since we're in the 2D plane, we can use k hat d sigma, where d sigma is the area element. This is simply going to give me, as we discussed, the area integral of partial x of n minus partial y of m d sigma, where d sigma in this case must be equal to dx dy. So this must be dx dy, because we're in the Cartesian plane. Okay, so how do you remember this? That's another thing. You remember this by simply remembering that you have partial, for the kth component, you have partial x, partial y, m, n, and 0. If I imagine that I'm computing the kth component, I get partial x of n minus partial y of m. That's how you remember this integrand. Now, what is partial x of n? Let's calculate them quickly. N is x squared, so I'll get 2x, and partial y of m is simply x. And this integral, this integrand is partial xn minus partial y of m, which is nothing but x. Now you see that computing an area integral over x is much simpler than having to find, dy for each of these 4 paths. I mean, you have to do 4 different line integrals. Instead, you're just doing one area integral. Now let's write the area integral in its full form. This is the region R. I'm calling this region as R. The region R of x dx dy. Now you have to separate. Suppose I call this integral, let me call this w, like work. So this is w. You have to separate the integrand from the region of integration, this R. how do you find the region of integration R, the limits of the integration? So I can see that x goes from 1 to 4. And what does y range from? Suppose I take a sliver. I take some point x. What are the ranges of y? Where does y start? Where does y stop? You can clearly see that y starts at 0. Where does y end? Suppose I have x equals 2, say. So the function here is y equals 1 over square root of x. So I'll have 1 over square root of 2. So if I take x equals 2, y starts from y equals 0 to y equals 1 over square root of 2. But in general, I'll have x. X won't be a certain value. X is just x. It can be anything in here, right? So in general, I'll stop at y equals 1 over square root of x. This is the entire thing. If I start from x equals 1 to x equals 4, you can see that I'm scanning this entire region. It's like I'm scanning this entire region. Okay, so now that we have defined the region of integration, I can just do it like this. I can just write the limits of integration. So I can say x equals 1 to x equals 4 and y equals 0 to y equals 1 over square root of x. Now you have the choice. You have the choice to do the dx part first or the dy part first. This is something we call iterations. Iterations means doing one thing after the other. You can do the x one first or the y one first. You're free to choose this. So this thing is simply x integral of dy from 0 to 1 over square root of x dx. So I'm just taking the y inside because I'm going to do this integral first. And as you can see, since this is a function of x, I'm going to get the result of the integration will be a function of x, and that should be inside the x integral. So it makes sense for me to do this first. But I can also do it the other way around. I can do x first, and then I can do y. It won't make a difference. I don't think it will make a difference. But let's not do that. I mean, in this case, let's do it this way. Okay, so what will I have? I'll have, this will be in y from 0 to 1 over square root of x. This is simply going to give me 1 over square root of x. So I'll have x over square root of x dx from 1 to 4. Right? This is coming from here, this square root of x. Now, w will simply give me integral from 1 to 4 square root of x dx, and this is nothing but 1 plus a half is 3 halves, so I have 2 over 3, x raised to 3 over 2 from 1 to 4. And if I do this carefully, I'll have 2 over 3, 8 minus 1. So I'll have 14 over 3. Let me just make sure this is right. Yeah, perfect. Okay, so this is an example of how to manipulate Green's theorem to do line integrals, specifically closed paths, line integrals over closed paths. Now suppose I'm not given a closed path, I'm given an open path, that is a path that doesn't close on itself. So this is going to be an example about that. And I'm given a nasty function, really nasty function, such that doing the area integral is not really healthy. So I have an integral like this, e raised to x cosine of y dx minus e raised to x sine of y dy. I'm not even showing you the path c here. Wait till you see it. So this is xy. The path goes something like this. I have a equals len 2. This is on the x-axis. I have point A. I have point D, which is at 1. D is at 0, 1. D is at 0, 1. and b is at minus len 2. So this is len 2, 0, this is minus len 2, 0. So the path is starting from a to d and then to b. Let's imagine what you have to do this integral in the old way, the way of converting y as a function of x, and then finding dy equals y prime x dx from the chain rule. I have two different paths, and I have to find these equations. This is equation 1, this is equation 2. That gives me the equation of the line, these straight lines. I have to find them first. I have to convert these integrals, and I'll have cosine of mx plus b because these are straight lines, and I'll have a really huge mess. But you're out of luck here because you have to do it. You have a field. I mean, you don't have a field actually. You just have some functions here. They're not telling you that these are fields, but there is an advantage to consider them as fields because you can use Green's theorem. But as I said, this path is not closed. You see, this is not connected in here. So what do we do now? Is there a way to get around this? Is there a way to use Green's theorem in this case? And the answer is yes, there is. We imagine that this path, this is our construction. Oops. We're just going to close this path. We imagine this is closed. And I have a region inside here called R. And now I'm going to use Green's theorem in the plane. So for this, f equals m n 0, where m is e raised to x cosine y, this one, and n is this, right? So now let me find the curl first, because, you know, as we saw in the previous example, at the end of the day, you have to do an integral over the curl, right? That's another way to remember this random looking expression. You find the curl, and the curl is simply partial x of n minus partial y of m. I'm just taking the kth component. So this is the kth component. And what does that give me? Let's do this quickly. Partial x of n, this thing, e raised to x, the derivative with respect to x is just e raised to x, and that is sine y, comes along for the ride. And you have a minus sign here, notice this, because n is this whole thing. This whole thing is n. So I have this as a partial x of n, and now I have to do this part, partial y of m. Now you can see that partial y will just ignore this, and partial y of cosine y is simply minus sine y. So I'll have minus, because I have this minus, be careful about the minus sign, and I have minus sine y, which is the derivative of cosine, and e raised to x just comes along for the ride. So as you can see now, the curl is 0, because you have plus e raised to x sine y minus e raised to x sine y. Together they give you 0. Now if you remember what I said, curl of f being 0 implies f is conservative. Now this is not what the question is asking you, but since this is conservative, we have a way inside this integral, this line integral, which is a nasty integration. Okay, so I'm just writing this for simplicity. I'm just writing this as m dx plus n dy, because I don't want to write those functions again. This is simply going to give me 0 if I have this closed path, C. Okay, so now the path goes from A to D to B to A again. So I can just separate this into two parts. So first one goes from A, D, B, the integral inside here, and the second one goes from B to A, the one which we constructed in blue. Let me just write this in blue so it, consistent everywhere. BA is the segment here, B to A, and I have the same integrand, and this thing is 0. Now this is the path we're given, right? ADB. This is the path we're given, the red bit. Again, for consistency, I'm just going to write this in red. Okay, so this thing is equal to 0 because, you know, by the Green's theorem, this is equal to the area integral of curl of f dA dot dA, actually no, n cap dA, and this is simply 0 because curl of f is 0. Now we can say that the required line integral over a dB f dot dr equals the integral of BA minus BA, because this is plus BA, which if you go to the other side you'll get a minus sign, BA f dot dr. Now this is a much simpler integral. I'll tell you why. Because you see that this is along the x-axis and y is constant here. I mean, y is equal to 0 in this case. If y is not changing, what can you tell? You can tell that dy is 0 because y is constant. And if y is 0, sine 0 is 0, cosine 0 is 1. So you only have to do this integral instead of going through two different line integrals, nasty little ones. I can just do this thing, integral minus integral, and look at this, b to a, b starts at minus len 2 to plus len 2. So I'll have the limits of integration minus len 2 to len 2 e raised to x cosine 0, which is 1, dx. And the y simply disappears because y is kept constant in this path. Now let's do this integration. It's quite simple. I'll have this thing, this is w, let's say this is w, a dB f dot dr, and this is simply plus integral of minus len 2 to len 2. Wait, do I have an extra minus sign here? I think I do, yeah. So this minus sign stays. So we have e raised to x dx, which is nothing but e raised to x minus e raised to x from minus len 2 to len 2. And if I do this, what do I get? Minus e raised to len 2 is 2 minus 2. Subtract this, so I'll get an addition, e raised to minus len 2. And e raised to minus len 2 is 1 over e raised to len 2, which is 1 over 2. That's by definition of len. E raised to len something is something. Okay, so this is w, the w that we need, the w from a, d, b, this one. Oh, this is becoming messy. Oops. Okay, anyway, so what is this? This is simply minus 2 plus 1 over 2, which is nothing but minus 3 over 2. This is our path. This is our work, or the line integral. So do you see any mention of fields in here? No, you don't. And you know, you have what was the complicated path like this, and you could simplify this largely because of Green's theorem. And even if this thing was not 0, you could still, this would have been simple doing this using the Green's theorem. So you should always, you know, judge a question and see what works best. In this case, Green's theorem was the best choice. In this case, just using this curl, the idea of a curl, was enough in this question to check whether f is conservative or not. Okay, let's move on to another question. Okay, this one is going to be okay, this is a continuation of this theme, finding the best way to do an integral. This time I'm being given an integral like this. So c x sine x minus y dx plus x minus y squared dy. Let's say this is w again, you know, because work is a line integral, the most famous one. So it's w, and this time this is a closed path, and I'm going to show you what the path is now, the path c. My path c is something like this. I have 0 0, I have 2 0, and I have something in between, 1, 1. The path goes something like this. Okay, this time you can use Green's theorem directly. Why is that? Because you have a closed path, right? You have a closed path with a region R. Let's say this is the xy coordinate. First thing you do while applying Green's theorem is to consider that this is a field. Oops. This is M, this is N, and F is equal to M, N, 0. The curl of F, that's how I remember the thing, partial x M N minus partial y of M. The kth component of this is nothing but, let's see, partial x of N. The only thing with x is this one, so this is the only thing that will survive. So I'll have 1 minus partial y of M. The only thing that has a y in this case is again this y, from which I'll get a minus 1. So together I'll get 2. So the curl of F is 2. Now I only need to do an area integral over curl of F dot n hat d sigma over this region R. But the curl of F and n hat is obviously k hat in this case because you're in the plane, and d sigma will be dx dy because again you're in the Cartesian system. So this is going to give me an integral of 2 dx dy over this region R. Now 2 is neither a function of x nor a function of y, so I can just take it outside the integral. 2 times integral of region dx dy. Now what does this integral exactly give me? We've discussed in the first lecture of this chapter that the area integral of 1 simply gives me the area of the region. And this is simply a triangle, right? What is the area of a triangle which has, in this case, base 2, height 1? Area is simply 1/2 2 times 1, which is 1. So you can directly say, without doing the integral, that this is 1, right? Because you have integral over the region of 1, which must give you the area. So we can clearly see that this W is going to be equal to 2. As simple as that. So in this case, if you're trying to do it using the line integral, you had to do 3 different path integrals. Instead, using Green's theorem, you just do just one area integral and you're done. This is the utility of the Green's theorem in the plane. As I said, the flux integral, again, I don't think in this course you do a lot of flux integrals. It's a similar thing. Instead of having, where is it? Okay, the flux integral is just this thing. You're just choosing a different integral. You're just choosing a different integrand, right? The process is exactly the same for computation. Well, anyway, that's enough, I think, you know what, let's do one more thing. I want you to know about this because, this is going to be important when you're doing electromagnetism or classical mechanics. You're given a field and you want to find the potential. I don't know, if you're studying a molecule and you're given some expression for F and you want to find the potential, because dealing with the potential makes calculating stuff about the system much easier. Like the example of the gravity, if you're moving from here to here and I want to find the velocity, the easiest way to do this is using the potential. Now let me give you an example of this. I'm given a force field that is like this. So x squared plus y squared I hat plus 2xy j hat. So this is M, this is N. Now I'm asked to find is f equals mn. This is a two-dimensional vector field. Is f conservative? If so, then find f equals gradient of f phi. You know what, let's choose this as v, as for potential. Okay, so find v. What is v? This is your question. First thing that you have to do, as usual, is find the curl of f. Let's do this quickly. We have curl of f, the ith component 0 minus 0, the jth component again 0, and again there is no z in here, so this is again 0. This is the jth component, and the kth component I have partial x of 2xy. Oops. Sorry about that. Okay, so I have partial. Okay, I was calculating the kth component. Partial x of 2xy is simply 2y, and partial y of x squared plus y squared is again 2y, but you have a minus sign because you're going opposite the diagonal, so you have a minus sign, minus 2y, k hat. This is 0, so curl of f is 0, which implies it's conservative. Now we're in trouble because the question is not over yet. We have to find the potential now. This was not a coincidence because I wanted the field to be conservative. I want to find the potential. Okay, so before I tell you how do you find the potential, there's a thing that I didn't tell you. For partial derivatives, if I have partial x or partial y of some function v, is the same as taking partial y partial x of v. So the order in which you do these integrals, these derivatives, is not important. In most cases, again, mathematicians can find v for which this doesn't work. But in physics, most potentials are well behaved, and so you can say partial x partial y of v equals partial y partial x of v. This is called associativity. No, it's commutative. So partial I is commutative. I can be x, y, and z. Okay, so how do I find the potential? The way I find the potential is by relating these things. So as we said, if f is conservative, if the field is conservative, it's gradient of some function v, right? So this is simply partial x v, partial y v, partial z v. So you have, this is equal to, f is given to you. F is x squared plus y squared, 2xy, and 0. Let's equate these things. Partial x of v equals x squared plus y squared. Now, how do I find v from here? You can do the most natural thing. Apply fundamental theorem of calculus, which is integrate both sides with respect to dx, with respect to x. What will I get? I'll get v, the integral of this is v, right? Actually no, because you're missing a constant. This is the most stupid mistake, and it's quite common actually, missing this constant. But in this case, this constant is not just a number like 1, 2, 3, pi, e. This constant can be a function of y. Why is that? Because you remember, if I take partial x of g of y, this is treated as constant because partial x ignores y and it gives you 0. You remember the story about the bear, right? The bear and e raised to x. The bear gets you at the end if you don't take care of these, these details. That c is just not just a number, it can be a function of y. Okay, let's do this integral. Integral of x squared is x cubed over 3. Integral of y squared, y squared is treated as constant, so I have integral of y squared dx. I'll get an x from here, right? So I'll have y squared x plus g of y. This is my v of x. Now, how do I find g of y? Y can be anything, right? G of y can be sine of y, maybe cosine of y. How do I do this? How do I find g of y? I use another one of these from these equalities, that f is equal to gradient of v gives me partial y of v equals, or the other way around, integral of partial y of v dy equals integral of this thing, 2xy dy. Now I can do this. Well, let's complete this anyway. I'll get integral of y is y squared over 2, so I'll get xy squared. Again, there's a constant here. This constant is, let's say, h of x, because this is an integration with respect to y, so the constant can be a function of x. Okay, so this is the other way around. But I'm not going to use this thing. I'm going to use something else. I'm going to use the fact that partial y of partial xv equals partial y of partial x of partial y v, right? But partial y of v is simply n from the force field. So what is partial x of n? N is 2xy, if you remember. So partial x of 2xy is nothing but 2y. And partial y of partial x of v of x, well, wait a minute, I made a mistake in here. So partial y of v, what is it? I'm going to substitute this v, x cubed over 3 y squared x plus g of y. If I do this v and I take the derivative with respect to y first, there's this part, what will I get? X cubed over 3, this gives me 0, y squared is 2yx, plus g prime y, the derivative of g with respect to y. Okay, so if I take the partial x of this, what will I get? 2y, you have this x, 2y, plus, I can't do this because g prime of y with respect, if I take the derivative with respect to x, I'll get 0, and this is going to be useless. Okay, so I guess I'm not going to use this. I'm going to go back to what I did before, which is what? Okay, so I'm back. Let me just continue where we left. So I have v of x equals x cubed over 3 plus y squared x plus g of y. Now, partial y of v is known to me. That's simply n, and n was 2xy. Now, this is what I know from our assumption. This is known. Now, if I do partial y of v on this v, this is what I'll get. I'll get 3 x cubed will disappear because partial y of x cubed is 0. I'll have 2xy plus g prime of y. So you see that I can cancel 2xy on both sides. This gives me g prime of y equals 0. And if I take the integral with respect to y on both sides, what will I get? I'll get g of y equals some constant. This time this is a real constant. This is not with respect to x, because we have already dealt with x. In this case, g is a pure function of y. We know this. There is no x involved. So in this case, it's a real constant. This constant can be 1, 2, anything. Okay, so what's our final answer? We know that g of y is a constant. So our final answer is going to be this thing plus a constant. This is our potential. Okay, so we have now almost finished the chapter on multivariable calculus. There's one small thing that I have to cover now. This is the del operators. If you remember, we haven't discussed del operations in different coordinate systems. We've only dealt with the gradient, the Laplacian, the divergence, the curl, and the Laplacian. These are the 4 del operations. In Cartesian coordinates, we haven't dealt with them in spherical or the cylindrical coordinates. So I've kept this till the end because it's not related to any other things that we touched upon so far. And this is really something that there isn't really a lot of theory behind this. You're just memorizing stuff. That's why I kept this towards the end of this chapter. Anyway, this should go with coordinate systems actually, because these are artifacts of being in different coordinates, as we saw, right? If you move from Cartesian to polar coordinates, the area element changes. It stretches. Sometimes it stretches, but sometimes it squishes. It depends, right? So because of this, you cannot really use the same formulas that you used for the Cartesian coordinates. For example, the gradient in spherical coordinates, it's not partial r hat plus partial theta hat plus partial phi cylindrical. Okay, in spherical, this is not the gradient. There are some factors that you have to take care of, and these are what we call scale factors. One important thing is that these scale factors fixes the gradient, because this is not the right expression, and we know this because we've tried, people tried using these definitions in their theories, and the theories failed. Mathematicians figured out that this is not the right expression, because intuitively the metrics of the coordinate, as we call it, they change. The geometry changes when you switch coordinates. And the scale factors is a fix for orthogonal coordinates. What do I mean by orthogonal coordinates? Coordinates which have bases that are orthogonal. So these include the spherical coordinates, polar, cylindrical, and Cartesian, the usual suspects. So this is a fix for orthogonal coordinate systems. This is something that you have to keep in mind. I cannot just give you a coordinate system UVW and tell you that you should use this one. UVW must be a coordinate system that is orthogonal. Only then this fix is going to work for you. Okay, so I want to introduce you to scale factors now. The idea of scale factors, I can illustrate this to you by imagining a coordinate. Say this is the Cartesian coordinate, and this is x, this is y, this is z, and I have some path in the Cartesian coordinate. So if I take a small element of this path, what will be the position vector? How do I find this? Now, if you remember, we said that dr was actually equal to dx I hat plus dy j hat, because you move certain distance in the x direction and the y direction, and if you know y is a function of x, you can find this exactly. The idea is exactly the same here. An arc length element is what we call this, is simply the vector arc length element is going to be simply ds equals dx I hat plus dy j hat plus dz k hat in the Cartesian coordinates. Now, how do I find this in the spherical coordinate or in any other coordinate system that is orthogonal? Dr r hat plus, there are some factors in here. I want to find these factors. D theta theta hat. Let's call these unit vectors like er. This is going to make things simpler later on. And d phi e phi. The idea is as follows. So dx, when you convert to r theta and phi, for instance, say this is xyz, and I want to put it, and I want to embed this in a spherical coordinate system. So what will this area element be in that case? Right? So the idea is that each of these dx, dy, dz, each of them are a function of r theta and phi. That's the idea. And we can use the chain rule from here. This is another reason why I kept this topic until here, because at the end of this chapter, because we haven't taken the chain rule until now. So I have partial x over partial r dr plus partial y, again partial x, I'm sorry. This should be partial x over partial theta d theta plus partial x over partial phi d phi. Now x, we know x in the spherical coordinates are cos theta, right? So I'll have partial x over partial r is cos theta dr plus, this is dx, the differential element of dx in the spherical coordinates. I'm doing a coordinate transformation right now, and you can see the Jacobian coming up. These are like the components of the Jacobian. Jacobian is intimately related with coordinate transformations, and this is something that you will really come to appreciate when you study tensors. Anyway, that's a conversation that will be had if you take the second course in mathematical physics. Well, anyway, let's continue here. Partial x over partial theta is minus r sine theta from here, d theta, plus partial x over partial phi is 0. Similarly, I can do the same for dy. What will I get? Since I want to shorten this, you can verify this, of course. I'll just give you the final results here. Dy will be sine theta dr plus r cos theta d theta plus 0, and dz will be, oh, it's not dz here, it's d phi. D phi will be, let's see, I have phi, which is minus sine theta cos theta and 0. So I must have, let's do this in detail actually. Partial, this should have been dz. dz equals partial z over partial r dr plus partial z over partial theta dr d theta plus partial z over partial phi d phi, where z is equal to r sine theta, right? So I'll have sine theta dr plus r cosine theta d theta plus 0. Is this right? Oh, I realized the mistake here. I've started with the spherical coordinate, but this should have been, in fact, the cylindrical coordinate. You see, for our example, I've chosen the cylindrical coordinate, not the spherical one. So there should have been a cylinder right here, not a sphere. Well, anyway, in the cylindrical coordinate, you don't have all of these because z equals z, right? So all of this is not really required. I just have dz equals dz. Now let's substitute this back now. ds equals dxi hat plus dy j hat plus dz k hat. Now if I want to substitute this back inside this equation right here, and I use the basis, like, you know, er is cosine theta sine theta 0 in the cylindrical coordinate. This is something that we took in the first chapter, and if I use these equations for the basis, er, e theta and e phi, I guess e theta was minus sine theta and cosine theta 0, and e phi, I mean ez was 0, 0, 1. If I use these, I'll find that ds equals r dr er hat, no, there is no r in here, r d theta e theta hat plus dz ez hat. Now this is what we call the scale factor. I mean, you have 1 in here and 1 in here, so h1, if I denote r as 1, if I denote r theta z as 1, 2, 3, the scale factors will be h1 equals 1, h2 equals r, h3 equals 1. So you see that the scale factors are related to the geometry of your coordinate system. And wherever you have the geometry, the Jacobian is going to show up inevitably. But we don't have to deal with the Jacobian in this course, for better or for worse. Now, okay, let me quickly give you the arc length elements in different coordinates. dx I hat plus dy j hat plus dz k hat. This is in the Cartesian. In spherical coordinates, I'll have dr er hat plus r d theta e theta hat plus r sine theta d phi e phi hat. So in spherical coordinates, you'll have h1 equals 1, h2 equals r, and h3 equals r sine theta. These are the scale factors. I'm calling the scale factors h. And as we just saw right now, in cylindrical coordinates, we have dr er hat plus r d theta e theta hat plus dz ez hat. Again, the scale factors, as I mentioned, are these. Okay, so what are the uses? I mean, what do you do with these scale factors? Here's the answer. I'll have the del operators, the gradient. The gradient in general, and of course for the Cartesian, h1 equals h2 equals h3, all equal to 1. This is for the Cartesian. So you can obtain the Cartesian gradient from this formula. I mean, you'll see that it's the same. Okay, so suppose I have the gradient of a scalar function phi. In general, this is going to be, okay, so it will be 1 over h1 partial phi over partial x1 dx1 plus 1 over h2 partial phi over partial x2 dx2 plus 1 over h3 partial phi over partial x3 dx3. Now I'm not really going to show you how you obtain this because we have to go through tensor calculus. I mean, yeah, so It's really not appropriate for this course at this level. And also we don't have time, so I have an excuse. Okay, so you can already see that x1, of course you should remember that x1, x2 and x3, these are nothing but x, y, z, or r theta and phi, or z, depending on whether you're in spherical or in the cylindrical. Anyway, but there is an actual reason why you have these scale factors, and it's and you won't be able to see it, unfortunately. Oops, I have a mistake in here. These shouldn't be dx's. I was confusing the chain rule here. So these should have been e1, e2, e3. These are the basis vectors in the coordinate system. Okay, so this is the formula for the gradient. Now we have 3 more to go, and then I'll give you an example illustrating the use of these scale factors. Well, anyway, the scale factors, you just remember these arc length elements, you memorize these for different coordinates, and the scale factors, you can just remember them from the arc length elements. Okay, so the next thing that I want to give you is the divergence in general. Again, I don't think you'll be asked a question like relate to these, but you'll have to know them. You'll have to know them for the future courses. Okay, so the divergence is usually you take the divergence of a vector f. You don't take the divergence of a scalar. It's not defined. Well, anyway, the divergence is h1, h2, h3, the product of these three, and I have partial x1 of h2, h3, v1 plus partial x2, h1. You can see that I'm not including h1 in here. Similarly, I'll not include h2 in here. I'm just taking the other two, v2 plus partial x3, I'll skip h3 here, h1, h2, v3. That's how you can remember this. This is the divergence in general. And if you substitute the scale factors, these scale factors, you'll see that you'll get back the divergence we defined in the Cartesian, in cylindrical, and so on. Okay, so there's one thing that I have to mention here. This quantity h1, h2, h3, in Cartesian it's 1. In spherical you have r times r sine theta times 1, the ones we found here. Yeah, these ones. If I multiply them, what will I get? In the spherical, I'll get r squared sine theta. In cylindrical, if you remember, I had 1, r1. Those are the h1, h2, h3. I'll just get r. These are in fact the volume elements. You remember when you have dx, dy, dz, the factor I have here is 1. Similarly, in cylindrical, I have r, dr, d theta, dz. This r is the same as this r. And same thing with spherical coordinates. You have r squared sine theta, dr, d theta, d phi. So this quantity, h1, h2, h3, is called the volume element. Anyway, this is something that I wanted to mention because it makes sense, because the volume element changes as well. And this is the factor, the h1, h2, h3. This gives you the factor by which it changes. And again, this h1, h2, h3 is related to the Jacobian. Well, okay, let's move on. Next thing I want to give you is the curl. The curl in any orthogonal coordinate system, for which the scale factors h1, h2, and h3. Again, the curl, you always take the curl of a vector, not a scalar. And again, you have 1 over h1, h2, h3. This one is perhaps easier to remember. You have h1, e1, h2, e2, h3, e3. And then I have partial x1, partial x2, partial x3. Again, partial x1 means I'm taking partial x1. This is the notation because it saves me time. Okay, then I have h1, f1. And again, f is something like this: f1, f2, f3 in some coordinate system, not Cartesian. And I have h2, f2, I have h3, f3. Okay, so this is the curl. And now the Laplacian. This is the last one. The Laplacian, you can take a Laplacian of a scalar. You can also take the Laplacian of a vector. This is one exception. Laplacian can be taken for both vectors and scalars. But in general, even in physics, you mostly deal with Laplacians of scalar functions, not vector functions. Okay, so the Laplacian is again 1 over h1, h2, h3, partial x1 of, again there's a combination here, h2, h3 over h1, partial x1 of u plus, again you see that you have in the denominator you have h1, in the numerator you have the other two. Similarly, you have partial x2, I have h2 in the denominator, I have h1 and h3 in the numerator, and then I have u, partial x2 of u. And the third one, quickly, is h1, h2 over h3, partial x3 of u. And that's it. These are the operators of del in an orthogonal coordinate system. This is really important. This fix with h1, h2, and h3, they don't work unless you have an orthogonal coordinate system. Some coordinate systems are not orthogonal. And as you study classical mechanics, hopefully in the next semester, you'll see that you might have a coordinate system that deals like this. So my coordinate system could be like of a planetary system. I'm dealing with the elliptical coordinate system. It's certainly not orthogonal. Well, anyway, this is these are the expressions. You just remember them. And remember, h1, h2, h3, they come from the arc length element. The arc length element being ds, these things. You should these are the most important things that you should remember: the arc length element, the scale factors, and the rest is just, you look them up. No one really memorizes these formulas, so I don't expect you'll get a question based on this. But anyway, I want to give you an example on this nevertheless. So this example, I'm being given a vector r equals x, y, and z. Now I have to calculate the divergence of r over r. So this is equal to the divergence of r hat. Now if I want to do this in Cartesian, the expression is quite simple, right? Or is it? Because r hat in the Cartesian is x squared, x, y, z over square root of x squared plus y squared plus z squared. It's a nasty little thing. Although the expression in Cartesian for the divergence is simple, partial x, partial y, you don't have the scale factors, but doing this on this, imagine doing the derivatives here. I remember actually solving it this way when I was taking 2 to 1, and it wasn't really fun. Now we'll do it using the scale factor thing. So I'll use spherical coordinates. So what is the gradient? The divergence in spherical coordinates? It's nothing but, let me just look it up. I'll have 1 over r. Anyway, it's a long thing. You don't really have to remember anything. Any of that. All you have to remember is that since you have r here, the components of theta, if you express this r hat in spherical coordinates, I'll have 1, 0, 0, because theta component is 0, phi component is 0. So this is what you'll get. And you can see from the expression of the divergence that these that these are 0. So only this thing will survive in the divergence. So what will I get? I'll get 1 over r, 1 times r sine theta. These are the scale factors, and partial r of, again, I'll have to leave out 1, so I'll have r squared sine theta times 1, because this thing is 1. The component v1, this v1 is simply 1. Okay, so what will I get here? I'll have partial r of r squared sine theta, which is 2r sine theta, divided by r squared sine theta. This is the divergence of r hat, and sine theta gets cancelled. I'll have r get cancelled out, 2 over r. Of course, r is not equal to 0, because that will give you a divergent answer. This is the answer. Simple. Just 2 steps and you're done. But with Cartesian, it's a nightmare. You have to deal with 3 different components, each of them equally nasty. But it's not that difficult, actually. I mean, it's still doable. Problem is, not everything is easier. Everything is actually harder. So the next thing I want to do is give you an example of curl. The curl of the same thing, r hat. Again, this is quite simple. I have 1 over r squared sine theta, which is h1, h2, h3. I have r hat, r theta hat, and phi hat. I have partial r, partial theta, partial phi. I have 1, 0, 0. Again, this is, I can do these stuff. I know that I have 0 r hat. Again, if I take the theta component, I have 0, 0. Everything is 0. So the curl of r hat is 0, which makes sense if you think about it. So I have the coordinate system like this. If I want to visualize what the field looks like, it looks something like this. R hat is pointing everywhere outside. It's the electric field of a point charge at the center. This is r hat. It's proportional to r hat. It's not exactly that, but you get the idea. So you can clearly see that there is no rotation. If I place a test charge in here, it will just go straight up anywhere in this. It will never, move around and make a circle like this. If I make a circle like this, if I take the dot product, it's 0 everywhere. So the work done is 0. For a closed path, the work done is 0. So this makes sense, because, this field is conservative then, by our theorem that we saw earlier today, which makes sense. And with that, we conclude this chapter. Thank you very much for listening, and see you next time.